Chapter 4, Section 1 deals with rational numbers. Your content objective says students will identify terminating and repeating decimals and use long division to convert rational numbers to decimals. The pacing guide claims this is going to be a 2-day lesson, but these are some pretty simple concepts. We'll see how long it actually takes us. In baseball, a batting average is a ratio of the number of hits a player has to the number of times it bats. Is typically written as a decimal rounded to the nearest thousandths. A player's batting average changes throughout the season as the number of hits and times at bat changes. So we're going to select the baseball player's card to view the career statistics, which means right there, and you can see on the back of that card where they've got the different batting averages on the right hand side for each year, how many times that he had at bat compared to how many hits. Suppose a player hits 32 hits with 60 times at bat. How can you find the batting average written as a decimal? These are the things we're going to learn about in this lesson, which, by the way, that player would have a whole lot better batting average than the one we just looked at. A rational number is defined as any number that can be written in the form of a divided by b, where both a and b are integers and b is not equal to 0. Now down the road we're going to talk more about why b can't be equal to 0, but if it is equal to 0, then you're going to end up getting what we refer to as a imaginary number. Looks like Shrew's getting down from his perch. We're going to select each card to see how it explains the rational number. First, negative 15. That is the same thing as saying negative 15 over 1. It is written as a fraction, a over b, where b is not equal to 0. Therefore, it's going to be a rational number. For this one, negative 8/10 is negative 8 over 10. It is written as a fraction where your denominator is not 0. It is going to be a rational number. Negative 1/8, written as a fraction where the denominator is not 0. It is going to be a rational number. And 28%, that's 28 over 100, written as a fraction where the denominator is not 0. So it is a rational number. So what is an example of a non-rational number, which we refer to as irrational? That would be pi. Pi is what we call a non-terminating, non-repeating decimal. We have patterns that go on through all time and eternity, and it never stops. It is going to be an irrational number. Our talk about it wants to know, is negative 5/6 the same thing as negative 5 over 6 and the same thing as 5 over negative 6? And the answer is yes. All three of those represent the same number. They're just three different ways of writing it. Our inquiry question says, what are the patterns in a decimal form of a rational number? So let's take a look at that. The first number we're going to look at is going to be 1 over 4. And you can see that 1 divided by 4 gives you 0.25, which is what we generally refer to as a terminating decimal. The textbook still considers this to be a repeating decimal because it repeats all these zeros after the 5. If you kept dividing, you just keep getting 0 there. So now we're going to take and set the fraction to become a negative 1/3 and see what happens to the colors when we do that. So I'm going to type my top one is a negative 1, and then my bottom one is going to be a 3. And when we do that, you can see that now we get a repeating decimal of 0.3, with the 3 being your repeating pattern. Pretty easy stuff so far. Let's look at another one here. For this one, we're going to do it as a 1 over 7. And when we do that, look at all the different colors here. Question is there a pattern? Well, watch what happens when I take my little dot and grab it and drag it out, and boom, right there. You see it? Orange, green, yellow, magenta, I guess, teal, and purple. You get the same pattern over and over again. If I was to go further out, you can see the same pattern comes up again and again. So you have a repeating pattern, therefore it is a repeating decimal. If we did 1 over 81 and looked at it, Well, that once again gives us a rainbow of colors, but if we kept dragging it out, eventually, boom, right there, we find that we have a repeating pattern in our decimal value where over and over again it gives us the same exact pattern of numbers dividing, so this too is going to end up being a repeating decimal. It says compare and contrast the decimal forms that you discovered in the Explorer and what do you notice? Well, I noticed that this one terminates or has a repeating zeros. This one is constantly repeating threes, and this one has a repeating pattern that we see over and over again. Name 3 different fractions that eventually repeat, then name the fractions. Yeah, we're not going to do that. Let's keep right on moving here. Now we're going to take and drag these fractions into the appropriate bin. Are they going to be repeating with lots of different numbers? Or, meaning non-zero digits, or are they going to be repeating with just zeros? For example, 1/2, that's going to be 0.5, a terminating decimal with nothing but zeros after it. 1/3, that's going to be 0.3 repeating. 1/5 will be 0.2. 1/6, I don't know. I have to look at that one. 1/10, that is going to be 1/10 or 0.1 terminating. I'm going to have to look up that one. That one's going to be 0.5, which is terminating as well. Now, for the rest, I'm going to grab my handy dandy pocket Satan here, and I'm going to say 1 divided by 6, which is a repeating pattern of 6's here. That 7's there just because it rounds up, so that's going to be repeating non-zero digits. Next, we're going to do 1 divided by 15, which gives us the same almost pattern, only now there's a 0 in front. I want to check that and make sure I did that right. 1 divided by 15. Yep, so that's going to be repeating non-zero digits. And finally, 1 divided by 32, and that one actually is going to terminate. You wouldn't think it would, but it does terminate. Now make a conjecture about the denominators of the fractions that eventually repeated zeros. What do you notice? And what they want you to type in here is this. You probably didn't catch this, but this is a really important thing. I mean, this is really important, guys. The denominators in everything that goes to zeros is divisible only by 2 or 5s or a combination of 2's and 5's. This here, that's got a 3. That's not going to be a repeating zeros. This one is 2 times 3. 3 is not going to lead you to repeating zeros. This one's got a 3 times 5. Once again, you have a 3 in your denominator. It's not going to lead you to repeating zeros either. And now we're going to get into some definitions. Any fraction can be expressed as a decimal by dividing the numerator by the denominators. Your first definition says the decimal form of a rational number is called a repeating decimal. Even the ones like 0.5 is technically a repeating decimal because it still has all those zeros repeating after it. Repeating decimals can be represented using bar notation. In bar notation, a bar is drawn only over the digits it repeat. Now let me go back to that concept of repeating decimals because this is the only textbook I've ever seen that does this. We're going to learn later about terminating decimals, and generally speaking 0.5, that's considered to be terminating. This textbook calls it both repeating and terminating because it repeats those zeros but it terminates in 5. Gets kind of confusing, doesn't it? After you get done with this lesson of this textbook, I'm going to say just know repeating and terminating is their individual values. Now we're going to take and move our slider here and take a look at what happens to these repeating values. Are you ready? Here we go. I'm going to slide it over. On the one on the top, you have your 4 repeating. So my bar notation would be written as negative 0.4 with a bar just over the 4. And for the other one, the 4-3 is my repeating pattern. So it's going to be written as 2.43 with a bar over both the 4 and the 3. You should already know this. That should be a straight up review from elementary school. Next, we want to drag each one of these boxes into their appropriate spot to match up the repeating notation. This one is the only thing repeating, so it's going to be 0.1. Next, you have 0.6111, so I got to find a 6 with a 1 in bar notation. That's going to become that one. This one, the 6 and the 1 repeat back and forth, so it's going to be that one. Next, I have a bunch of zeros that repeat, which is going to be that one. Yes, I know it looks really weird, putting a bar notation over a 0. That's what the textbook says to do. And then here you repeat in patterns 161, 161, 161. So that one is going to take and go. Let's see if I can catch it and drag it down there. Boom, right there. Easy math. Anybody can do this stuff. And now they give us the definition of a terminating decimal that says every decimal is a repeating decimal because of those zeros. However, decimals with a repeating digit of 0 are called terminating decimals. The repeating zeros in a terminating decimal is usually truncated, which is a fancy word for dropped. For example, the terminating decimal 0.250 repeating is just 0.25. Now your textbook wants you to write 1 over 40 as a decimal and determine whether or not the decimal is going to be a terminating decimal. So how are we going to do it? First off, can you predict whether it's going to be terminating or repeating? Well, think about 40 is the same thing as saying 2 times 2 times 2 times 5. So you got 3 2's and a 5. If all you have are 2's and 5's that multiply together to equal 40, then you know it's going to be a terminating decimal. And now we're going to take and prove it. They're going to use long division and divide 1 by 40. And when they do, well, that doesn't look very pretty. There it is. They ended up getting 0.250 with a whole bunch of repeating zeros afterwards. And because of that, we're going to answer that the answer in simplest form is going to be 0.025 right here. So it will indeed be a terminating decimal. Let's keep going. Part B says right here the problem ends in repeating zeros, so it is a terminating decimal. Yes, it really is this easy to do these problems. Now it's going to be your turn to work this problem out. Write 3/8 as a decimal and determine if it's terminating or repeating. But before we even get started, what would 8 be factored? 8 would be 2 times 2 times 2, because 2 times 2 is 4, times 2 is 8. All you have is 2's, so right there we know that it is a terminating decimal. You pause the video and solve the rest of the problem. Divide that out using long division. Did you get it done? The fraction is 3 over 8, which means we're going to put our first number in the house, just like I've taught you. 3 goes in the house, 8 goes outside the house, 8 goes into 3, 0 times. Annex in your decimal and your 0 with your decimal going up. 8 goes into 30, 3 times, which is 24. That leaves 6 left over. Annex in another 0 and bring it down. 8 is going to 60. Well, let's see, that's going to be 7 times, which is going to be 56 with 4 left over. Annex in another 0 and bring it down. 8 goes into 40 5 times, which is going to be 40 with nothing left over. So our answer that we're going to plug in here is going to be 0.375. Check that one, it checks. Check this one, it checks. Easy math. Long division's a little bit tough, but I'm confident that if you try hard, you'll be able to do it. But what if we ended up having a negative number? It really is not going to have any effect on the problem whatsoever. We're going to work it the same exact way where we're going to use our long division. And when we come back for part 2 of this video, I will show you exactly how to do that.